Hey everyone, and welcome. Today we're jumping into one of the most powerful and, let's be honest, one of the coolest tools in all of mathematics, the cross product. This is a story all about vectors, about twist, and about how two different directions can team up to create a third, totally new one. But let's start with a question. Have you ever looked at something like a gyroscope spinning like crazy and wondered how? How does it stay so perfectly stable? How can we even begin to describe the invisible force of something turning? Well, to really capture the essence of a spin, you need a very special way to multiply. All right, let's get into it. When it comes to multiplying vectors, it turns out you've got options. You've probably met the dot product before, but today we're talking about its much more mysterious and frankly fascinating sibling, the cross product. It's really a tale of two very different products. And here is the absolute key difference. The dot product, over on the left, it just answers a simple question. How much are these two vectors pointing in the same direction? And the answer it gives you is just a single number, a scalar. But the cross product, that's a whole different ballgame. It doesn't give you a number. It gives you a brand new vector, a third vector with its own length and its own direction. And believe me, that is a huge deal. So if the cross product gives us this whole new vector, what is that vector all about? Well, it's really defined by two key things. First up, we've got to figure out how long it is, or, as we say in math, what's its magnitude. Now, this is the really beautiful part. The length of this new vector isn't some random abstract number. It has a real visual meaning. The magnitude of A cross B is exactly the area of the parallelogram that you could draw using vectors A and B as its sides. So, the more spread out those two original vectors are, the bigger the area of that parallelogram, and the longer our new vector is going to be. Simple as that. And you can see that perfectly right here in this chart. When the vectors are parallel, pointing the same way, there's no parallelogram to even speak of, right? It's squished flat. So the area is 0 and the cross product's magnitude is 0. But as you increase that angle between them, the area gets bigger and bigger until it hits its absolute maximum when the vectors are at a perfect 90-degree angle from each other. Okay, so we've got the length of our new vector figured out. That's half the puzzle. But that's only half. The other half is, which way is it pointing? And this is where things get, a little hands-on. We need to find its direction. And we do that with the famous right-hand rule. Now seriously, I want you to actually do this with me. Take your right hand, point your index finger along the direction of that first vector, A. Now curl your other fingers in the direction of the second vector, B. Go on. The direction your thumb is pointing? Bam! That's it. That's the direction of the cross product. And notice, it's always sticking straight out, perpendicular to the first two vectors. And I really mean it. You gotta do it yourself. There's a fantastic professor, Professor Leonard, who always says this when he's teaching it. He says, seriously do it. You look at me like I'm an idiot. And he's totally right. Physically going through the motions is, without a doubt, the best way to get a feel for where this new vector is going to end up. All right, let's put the two pieces of the puzzle together. We have the magnitude, which is the area. We have the direction, which we get from our right hand. Now we can finally define this new thing, our resultant vector. So here it is, the grand takeaway. The cross product takes two vectors, A and B, and it spits out one single new vector. And this new guy has a direction that's perpendicular to both of the original ones, and a length that is exactly equal to the area they form. It perfectly captures their relationship in 3D space. Now this definition leads to some really wild and interesting properties. The first one and the third one, we've pretty much covered those. But look at that one in the middle. Anti-commutative. Now think about normal numbers, right? 3 times 5 is the same as 5 times 3. No big deal. Not here. No way. With the cross product, the order you multiply on is absolutely critical. A cross B points one way, but B cross A points in the exact opposite direction. Okay, that's a lot of abstract geometry, I get it. You might be wondering, why did we even bother inventing this thing? Why does any of this actually matter? Well, let's pull this out of the world of pure math and back into the real world. Because it turns out, the cross product is the language of physics, especially for anything that rotates. Torque, that twisting force when you use a wrench on a bolt, that is literally defined as a cross product. And angular momentum, the very thing keeping our gyroscope from falling over, also a cross product. It's the perfect tool for when two forces combine to create an effect in a totally new direction. And that brings us full circle. Right back to our spinning gyroscope. The reason it seems to defy gravity, the reason it stays so stable, is because of something called angular momentum, which we call L. And how is it defined? As the cross product of its position r and its momentum p. That new vector that gets created, L, points straight up along the axis of the spin, creating that incredible stability. It's not magic, it's just the cross product doing its job.
So you see, the cross product is way more than just a formula in a textbook. It's a fundamental idea. It describes how an interaction happening between two things in a flat plane can create a result that literally emerges into a third dimension. It's the mathematics of twist and turn and rotation. And that kind of leaves you with a final thought, doesn't it? Where else in the world all around us might this incredible principle be hiding in plain sight?